Hey everyone, welcome to the channel and to the very first video in our Databricks series. Have you ever wondered why Databricks exists or how it handles massive amounts of data so efficiently? You have probably heard terms like data lake, data warehouse, and now even lake house. But what do they really mean? And why do we need something like this? In this video, we are going to break it all down. We will start by understanding the basics, what data lakes and data warehouses are, and how the concept of lakehouse architecture brings the best of both the worlds. Basically, why lakehouse architecture matters. Then we will dive deep into Delta Lake, which is the backbone of Databricks. We will explore its key features like ACID transactions, time travel, schema enforcement and evaluation, difference between managed and external tables, and how the vacuum operation helps keep your data storage clean and efficient. By the end of this video, you will have a clear understanding of the challenges Databricks was designed to solve and how it empowers modern data teams to work faster and smarter. And I would recommend you guys make some notes as well as we go along. It will help solidify things, and you can always come back to the video later if you need a refresher. So let's get started. So our story starts from data warehouse. What is a data warehouse? It is basically a centralized repository for structured and organized data, which is optimized for your analytics and reporting tasks. You can use tools like Tableau and Power BI for creating reports and for business analytics. Company likes it because the data is clean, stored in a structured format, easy to query. The query runs faster, and it is good for business analysts and dashboards. Some of the examples of data warehouse are like Amazon Redshift, Google BigQuery, Snowflake, Azure Synapse Analytics, right? But there are some downsides as well. It is expensive to scale. It is poor at handling unstructured and semi-structured data. It is less flexible because you need to model your data upfront, because as I said, data in data warehouse is stored in structured format, so you need to model your data. You have to apply ETL and on your data, and yeah, that makes it less flexible. It is not good for ML or data science workflows because machine learning often involves working with large files like images, videos, audios, or huge logs, which is basically your unstructured and semi structured data. And data warehouse is not designed for this. Streaming and real time data often needed in ML use cases, which is also again difficult to integrate in data warehouses. And also in machine learning workflows, you often need to experiment with new data. You want your data in raw format, right? Because you need to experiment with new fields. You want to join diverse data sets or work with, you have to basically work with raw format, which is not possible with data warehouses. So these are few downsides of data warehouses. And with the rise of big data, we started getting data in the form of videos, text, images, logs, right? So that's when the concept of data lake came into picture. Think of data lake as like a huge folder where you are basically holding all types of raw data, structured, unstructured, semi-structured data. You basically dump everything into data lake. Company likes it because it is super cheap and scalable, easy to handle large volume of diverse data, and you basically don't need to know the schema upfront. So you close your eyes, you dump everything, and that's data lake. But That's the also it brings some problem, like if you will keep dumping everything, then in no time it will become a mess, because and then it will be hard to query. So that is one of the problem with data lake. And there is no guarantee of data quality, governance, or performance. When I say this, what do I mean by this line? What do I mean by this is data lake lacks data quality because data lake store raw data as is without checking if it is complete, consistent, or correct. So there is no validation. It is easy to end up with dirty data or missing fields, inconsistent formats, and without quality control, basically business users and analysts can't trust this data for some critical decisions. And it lacks governance because governance includes things like access control, lineage tracking, and compliance. Data lake often don't enforce these by default. There is no standard rules or policies. So and it also makes it difficult to audit. So you don't know who accessed what or where the data came from. So there is some security risk also involved because sensitive data might be exposed to the wrong people without proper controls. Guarantees also because since data is raw and not indexed or optimized properly as we would be doing this in data warehouse, query can be slow, especially on large data sets, right? And data scientists had to write a lot of complex code to get usable data from it. So these are some of the problems we faced in data lakes. So now you uh, see the problem here, like now we have two systems, one to store raw data like your data lake, and one to analyze clean data, which is data warehouse. But both are disconnected. You have to basically copy data from your data lake to warehouse if you want to do some analytics, workflows, or do some reporting on that. So there is the possibility of data duplicacy, latency, and you will write complex pipelines to do this. And your for your machine learning engineers, data scientists, data lake is what they need, and BI, for BI tools they need data warehouse. So to solve this problem, lakehouse came into picture. So lakehouse, what it does, it is basically taking the best of both the worlds. It is combining the feature from data lake and the feature from warehouse. So it stores raw data like your data lake, but query and manage it like a warehouse. So one system for all the workloads for your BI, machine learning, streaming, batch processing, right? So how does it work? It is basically adding some features on top of your raw data storage. So your base layer is data lake, and it adds some features like ACID transactions, atomicity, consistency, isolation, durability, and it brings schema enforcement and evolution, data versioning and time travel, performance optimization like caching, indexing, Z ordering. And so this is on top of your raw data storage. And who made it happen? Databricks built Delta Lake, which is an open source storage layer, to make Lakehouse real, which brings all these different features to your data lake. Okay, so this image I took it from the official website of Databricks. Let me show you once as well. So if we go here, then yeah, you can go through this article and get more information on this. Okay, and okay, then now let's get back to our slides here. So on the left we have, let me turn on the laser. On the left we have data warehouse. Okay, so here we deal with only the structured data, which is your transactional databases like MySQL, Postgres, which is commonly used for day-to-day operations. Data goes through ETL and is loaded into data warehouse, These warehouse primarily supports BI and reporting, nothing more. It's optimized for your analytics, right, but not flexible or for diverse data types. Then we have in the middle we have the data lake. So this can store all types of data, structured, semi-structured, unstructured data, which is like video, logs, images, audio. And ETL processes load data directly into the lake, and from there it can serve to multiple consumers. BI and reports might still need a data warehouse built on top of this data lake, which goes through this ETL, while data science and machine learning teams can directly access raw data or processed data from the lake. But notice here multiple paths, which brings more complexity, and data silos can form easily. When I say data silos, that means like different teams like BI analyst, data scientist, machine learning engineers often build their own separate data pipelines to access the data they need. For example, BI teams might transform raw data into structured format, right, and load it into a warehouse for reporting, while data scientists might pull the same raw data directly into their notebooks or tools for modeling. So over time this could lead to multiple copies of the same data, right, so which is your basically data silos. And the problem it can cause is duplicacy, inconsistency, like governance issues. So the and maybe, yeah, increasing cost as well. So that is one issue. And now on the right we have data lakehouse, so which is basically the best of both the worlds. It is built on top of your data lake. So the base layer is data lake, and it adds a metadata and governance layer. uh, it means it supports data reliability, ACID transaction, schema enforcement, and other features that traditional warehouse offer, but with the scalability and flexibility of a data lake, right? And one of the biggest advantage is like all your consumers can now access data from a single unified source. So the problem of duplicacy is resolved here. No duplicacy, no silos, just one layer for all the consumers. So that's the advantage of using data lakehouse. Okay, so let's understand what is a delta lake here, because in this slide I am saying like Databricks build delta lake to make lakehouse real. So let's understand what exactly is delta lake. So in short, when you are writing data into your storage, cloud storage, you are basically writing data in a Parquet file. And when you will define, like when you want, while writing you will define like you want to write in delta format. So additionally a log files gets automatically created into that bucket. Okay, and that log is nothing but your transaction logs. So it sits on top of your delta lake, sits on top of your cloud storage. It is an open source storage layer developed by Databricks that brings ACID properties, which ensures data reliability during concurrent read and write operation, brings security and performance to your data lake. Okay, so your backend storage, cloud storage, is just like a plug and play, but the main features it brings is your transaction logs, schema enforcement, evolution, time travel, interoperability. Means it is not just with, not used, data lake works not just with Databricks but also with Apache Spark, Athena, EMR, and more. That's the power of the open source delta. Okay, so we will see these features one by one in the next slides. Okay, so if we move forward. Okay, so this is an important slide, and if you understand this slide, then the next couple of slides will be easy to understand. Okay, and I hope you guys are also writing some notes. Okay, so what are we doing here? So let's suppose you want to write data in your S3 bucket. You are saying I want to write data in delta format. You are saying I want to write data in delta format in this S3 path. Okay, and this is the mode, like you are choosing to mode overwrite. So here we are writing an unmanaged delta table, which basically means there is no Hive meta store required. Okay, so what do I mean by this line? So let's understand first what is a meta store. Okay, so a meta store is basically a database that stores metadata about your data tables, not the data itself, but the information about your data. Okay, for example, your table name, table schema, which is your column names and types, table location, where the table is stored basically in S3 or DBFS, or and your partition information, data format, whether the data is in Parquet or CSV, etc., when it was created. So these kind of information is what we say metadata, which is basically the data of your data. Okay, it's basically the information about your data. Okay, so your meta store stores the metadata information, and some example of meta stores are like Hive meta store, which is used by Spark or Hive, etc., and AWS Glue catalog is another example, which is a managed meta store in AWS. Unity catalog is an example, which is the centralized governance plus metadata across clouds. And Apache Iceberg and Delta Lake, which can work with or without metastore. Okay, you need metadata to query and manage data properly. Okay, so Data Lake is saying I don't require a Hive metastore. Okay, why it does not require a Hive metastore? Because when you are writing data in delta format, it is basically writing your data, which is your Parquet file, and it additionally also creates a delta log in your S3 bucket. And this delta log is very important. It stores the transaction logs. So this delta log is basically a folder which will automatically be created in this S3 path, which contains transaction logs, which is basically some JSON files that record every change to the table, enabling ACID transactions by tracking commits, ensuring consistency, and allowing isolation and durability of operations. Okay, so Delta Lake's engine uses these logs to implement ACID properties. That's why Delta is saying they don't rely on the metastore, because they have their own transaction log for ACID and file management, right? Therefore they are saying like they don't rely on the metastore, which is reducing the need for a metastore but not entirely removing the need for a metastore. Okay, this point is important because you would still need a metastore if you want to register your delta table as SQL table. And why do you want to register your delta table as SQL table? So that you can uh, use your data table with the select statement, like select star from my table. You can give a table name to it, otherwise to access that. Otherwise every time you want to access, you have to give this whole S3 path, right? So to avoid that and to register your delta table as SQL table, you would still need a metastore. And this will also give you features like table ownership, access control, and data catalog, right? So so yeah, with this transaction logs, Delta is basically saying we don't rely on metastore, which is just reducing the need of a metastore. And that's why it is an unmanaged delta table, because there is no Hive metastore involved. Okay, so I hope this line is clear. Now you have a delta lake table at this path. Okay, like we are saying like delta lake table. Okay, even though we are saying it delta lake table, yeah, doesn't matter if we are not explicitly writing create table. Okay, so still we are saying it as unmanaged delta table. Okay, Delta does not need a meta store to apply acid. It just need the delta log. Okay, because this meta store was providing us the acid properties, but delta is saying I don't need meta store to apply acid because I already have this delta log with me. Inside delta log folder, this is a folder, we have transaction logs. Okay, so when you will write this, you will see something like inside this s3 path, you will have a parquet file, and you will have this another folder, and inside this folder we have this json file. So when you are writing data in s3 for the first time, delta lake automatically logs it, hence this 000.json. So what is stored in this json file? This stores information such as which file are you writing, what is the schema, okay, and what operation did you perform uh, on this path. Okay, so different operations like did you write your data, or did you do this create table operation. Okay, so this delta log is an append only log. So whatever you will do, whatever transaction or whatever operation you will perform on this s3 path, everything will be appended. Okay, and this is important because you can audit all changes on your delta table over time. It will be helpful for debugging or data lineage, data governance. It will help you track who did what and when as well, like if you also enable logging with user information. That's why this is one of the important field in your log entries. And before delta lake, spark tables were often created as hive tables. Okay, so you had to register table in a meta store so that tools like spark could understand where to find the data. Acid guarantees and transactional tracking could be managed. You could use sql to query your tables. Okay, and why it is useful? Because it makes it easy for the engines like spark to discover and query data. It keeps everything organized, and yeah, even across many data sources. It enables sql like access, right? So that's why it was useful. And just for the sake of argument, let's suppose you don't want to create this meta store. Okay, then what will happen? Okay, so then there will be no globally registered table name, no persistent schema. If someone writes new parquet file with different schema, spark may infer it incorrectly. Means let's suppose you write some data in your s3 bucket. You write one parquet file with two columns, let's say id and name in your s3 bucket, and then you read that data, and then you again write another parquet file with a third column in the same s3 bucket. Nobody will stop you. You could able to write that in that s3 path, but then when you will read again data from that s3 path, spark may infer it incorrectly, because now we have two parquet file in the same location. One parquet file has two columns, another parquet file has three columns. So then spark may infer it incorrectly. So this is a problem. And no column type enforcement. So schema evaluation is risky here. No central governance, access control or auditing could happen. Okay, and cannot write usable sql queries like select star from this table would also be not possible if you don't want to create a meta store. Okay, let's suppose you want to read that without meta store, you would always have to specify the path, and spark would infer the schema each time, right? Because now you don't have a table name, you are every time you want to read, you are specifying the whole path, which makes it slow, right? And what will happen if you create a meta store? Because now if you have a meta store, you registered a table once, you just have to register the table once. Okay, so like for example, like you will do create table, uh, yeah, create table command basically. So now anyone can query your data using SQL. Schema is consistent, right? Table metadata is cached and accessible, right? So these are the, and it will also help in auditing, right? So these are some of the benefits which you get from metastore, right? If you create a metastore, and generally that is important, or like good practice to do that, especially in your production, and when you collaborate with different team members, or to have a SQL based environment, you usually need a table abstraction uh, which a metastore provides. And acid we already know. uh, Atomicity, which is basically saying the operation is either fully succeeded or fully failed. Consistency, which says that data will always be in a valid state. I is for isolation, which is telling that concurrent read or write don't clash. Only the latest valid commit is visible to other queries or users. D is for the durability. Once the data is stored, it is safely stored. Okay, so when you did df write format delta, then what happens? Delta enforces schema. Delta does time traveling. uh, how it does time traveling? Because remember I told you, like in this slide I'm telling like every operations which you are performing is append only, so everything will be appended in your delta log. So now as everything is getting appended, you can basically go to the previous version using version as of. And what's the role of create table? A metastore entry is getting created for that path, and so that you can use now SQL to query that table, right? So now these lines should be clear. And so create table doesn't start the delta magic, but it already started when you did your write format delta. Okay, and delta tracks every subsequent write that we already discussed, right? Delta tracks every subsequent write to the same S3 path as long as you are writing using format delta. So your second write triggers a new delta log version. uh, and for example, if you are reading that file from this path, and suppose you added a new column and you are writing again in delta format to the same S3 path, then what will happen? A new parquet file will be created, and then there will be a new JSON file in your delta log, but this time it will be 0001.json, right? Old delta file may be garbage collected later if we do vacuum. So this is also we will see in our practical session. If we do vacuum, then basically what delta does, it removes the old version, right? So we have to be very careful when we do vacuum. And yeah, we are writing again, and then acid applies again, right? So now this should be clear. And so we have now understood the delta, how delta works on S3. Now let's understand what happens when you do create table. Okay, so where is table in all this? SQL queries runs on tables. So who is creating the table? How is it connected to the delta data stored in S3? So now let's understand what table is actually is in the context of Databricks and Spark. And there are basically two kinds of table. One is called managed table, and another one is external table. Okay, so now let's understand what does this mean. Okay, so before uh, discussing this slide, let me show you the next slide for an example. So here we have a manage table. So in manage table we are doing create table, and we are basically defining our columns, and we are saying using delta in the manage table, right? Using delta. While in external table we are also defining a location. So here we are controlling the exact data path, right? So we are saying like, okay, create my table, but the location where my data is here. Okay, Databricks stores only metadata pointing to this path. Okay, but in this manage table, data is stored somewhere like user hive. So it is stored in your Databricks itself. So your delta log and parquet files will be inside that directory itself in your Databricks. You don't control where it lives unless you go looking for it. So this basically, this path is decided by Databricks, so you have to like search for it where it is stored. I mean, yeah, so you don't control the path, basically. That's what it means. So if you run drop table this customer, then your entire data plus metadata is gone. Okay, this is what is happening in your managed table. But in external table, because you are defining this location, Databricks is storing only metadata pointing to this path. Okay, you can update delete from SQL, and S3 content will also change. So if you perform this update or delete command in your Databricks from SQL, your S3 content is also changed. Basically, you will see a new parquet file in your S3 bucket. Okay, and if you do drop table, then your metadata is removed, because your metadata is stored in Databricks, but your actual data is in S3. So it says metadata is removed, but your S3 file and delta log will remain as it is. So you can even recreate your table again, because your S3 file and delta log is safe. So I hope now this gives you a basic idea of what is a managed table and what is an external table. Now if we go back again, so it says it's just a metadata stored in Hive Metastore or Unity Catalog. We will learn about Unity Catalog in our future videos. So a metadata stored in Hive Metastore pointing to schema, data location, Hive file format. We have now discussed all these things. So this line should also be clear to you. So who owns, and this is just a table representation of what we just discussed. So in managed table, Databricks manages the data location. External table, you are managing the data location. So your location is not specified, stored in default warehouse location in your Databricks, and you are specifying the location. When you do drop table, then deletes actual data plus metadata. But with external table, after dropping, you delete only metadata and data stays in S3. Managed table is common for internal pipeline staging temporary data sets, and external table is common for your shared data sets, delta lakes, external S3 data. Okay, and now, okay, so moving on, this we are seeing some features. So ACID transaction, we already discussed what this ACID transaction means: atomicity, consistency, isolation, durability. So the next one we have is the schema enforcement and evolution. So this is another feature which Delta Lake provides. So schema enforcement is basically, let me first give you this example. So let's suppose we have this table where we have this ID and name. Okay, and now if you do this operation, spark create data frame, you are creating this new data frame with a new column email. Okay, if you will try to write this new data frame directly without using this option, then it will not let you write, because the schema is not matching. And to write that, you have to basically enable this option. You have to write this option like merge schema true. You are saying that, okay, I want to merge this schema with this new column, then only Delta Lake will let you write this new column. So basically you are enforcing the schema here, right? And yeah, so this is basically an example of schema enforcement and evolution. So if you will think that what happens to the new data, then the other values will be null, the new entry will have this data. So this is one option, merge schema. And let's suppose you are not writing a new column, but you want to change this ID from integer to string. Okay, in that case also your schema, if you're not defining merge schema, or there is one more option, overwrite schema, then Delta Lake will not let you do that. Okay, so if you want to change the schema of this one, you are basically not adding any new column but just changing the schema. Then you would say, okay, I want to overwrite my schema. So instead of merge schema, you can write overwrite schema true. Then this can change to the other string format. Okay, so now let's read what we have written here. So for schema enforcement, Delta Lake will block any write if the incoming data does not match the existing schema unless evolution is explicitly allowed. Schema evolution, if you enable it, like merge schema is equal to true, Delta Lake will automatically update the table schema to accommodate new columns. Okay, that's what we discussed. Delta Lake enforces schema to maintain data quality. If you try to write data that does not match the existing schema, the operation will fail. However, Delta Lake also supports schema evolution, allowing you to update the schema as your data changes over time. Okay, now I hope this is clear. We will see this hand in our next practical session also. Okay, and time travel, another feature of which of Delta Lake. So basically now we know every operation we perform, the we will get new parquet files will keep on appending, and in Delta log we have our transaction logs where we have the JSON files, so it will keep on appending. Okay, and because of that append, you can basically do operations like this, like you want to read in format delta option timestamp as of this, you want to read this data from this path, or you can also write it like version as of 5. Suppose now you have done 5 operations, suppose now you have done 7 operations on your S3 path. Okay, and your latest version is 7, and then but you can go back to your 5th version and you can load the data again, right? So this is basically your time travel. And now let's just also read here what's written. Delta Lake's time travel features allow users to query historical data states by maintaining version snapshot in the transaction log. Okay, each write operation creates a new version, and users can access older version by specifying a timestamp or version number. This is useful for auditing, reviewing historical data changes, debugging rollbacks, reverting to a previous state in case of some error while write, reproducing analysis or historical analysis, basically comparing data across different time periods. So this is also a very important feature which Delta Lake provides. Moving on. Okay, so here we have now Databricks, some description, some notes on Databricks. So it is basically the pioneer of the lakehouse concept, built on Apache Spark distributed data processing engine, which is Apache Spark is a distributed data processing engine. Allows data engineers, scientists, and analysts to collaborate in a single platform, offers notebook, automated jobs, data pipelines, ML models, and more. And what problems does Databricks solve? So it unified data platform, no more jumping between tools, right? Massive scalability with Spark, easy for collaboration, shared notebooks, so we can have shared notebooks as well in Databricks. Built-in versioning, governance, and lineage. Here is a brief, very high-level distinction between Azure Databricks versus Databricks. I don't work on Azure, so it is just a very high-level difference. Okay, I mean, so Azure is basically a managed version of Databricks on Microsoft Azure. Same core platform but tightly integrated with Azure services. Okay, that's the very high level description of the difference between Azure Databricks or versus Databricks, in case you are wondering, right? So features like hosting in standalone, you can take any cloud platform, but in Azure only Azure. Authentication native or IAM here, Azure Active Directory. Storage could be from anyone, from any of the cloud platform, but here will be specific for Azure, and same for billing. Okay, and so yeah, now we have reached to the summary of what we have learned so far. So we discussed about data warehouse. Initially we had data warehouse, then data lake, then we also understand what is a lake house and how it brings the best of both the worlds together. So data lake was cheap, flexible but messy. Data warehouse was clean, fast but rigid, as it was only for structured data. Lake house, which brings the best of both world. And then we talked about features of delta lake, and Databricks is basically a platform built for the lake house. Then we saw very high level distinctions between Azure Databricks and Databricks, which is, yeah, Azure Databricks is the Databricks inside Azure. So that's all for this video, and I hope you guys like this. And if you have any doubts, or if you want me to change the style of explaining, then please let me know in the comment section. And because this is the first video of this channel and also in our Databricks series, so I might have yeah just let me know in the comment section, like how did you like it. And in the next video we will see some hands-on practical, so all the features which we discussed here, we will also try to see that practically. Okay, so we will create a Databricks notebook, we will create a read a file, and we will try to see how the transaction logs are getting changed and how time travel is happening. So all these things I will try to cover in the next practical video. And so my idea was to separate this theory video and practical video, and not to create a very not to create like a very long video of combining both, or only a practical. So let me know what is your suggestion, what would you like to see more, or if you want me to change something in the video, and if you have any doubts, and if I could not able to, if you like, if I could not able to explain anything properly, or if you still have some doubts, then let me know in the comments and we will try to solve that together. And yeah, so you know what, if you liked it, if you like the way I was explaining, or if you like the concept, if you then support this channel by giving me a like, subscribe to the channel if you would like to know more about, if you are interested to know more about Databricks or data engineering. In this video, in this channel, we will also post about data things related to things needed for data scientist role. And we will also post, yeah, different things. Maybe let me know if you would also like to see videos on SQL or PySpark. Then based on that I will prioritize like which topics to cover. Yeah, because this is just the beginning, we will try to cover a lot of things here. And yeah, that's it for this video. Have a nice day and see you in the next one. Thank you. Bye.